This work was originally presented at the AIM 22 conference, and it's been slightly expanded for today's talk. Okay, first, to break down this mouthful of a title. There we go. The core work, embedding soft synergies into soft materials for interesting compliant robotic hand grasping. What does this mean? First, the embedding of soft synergies will be covered during the motivation. What are these soft synergies and why do we want to embed them into hand? Next, why do we want soft materials? Why are the advantages of this, and what was the design process that allows this? And finally, the results. We obtain a robotic hand that is slightly creepy, but it has embedded synergies and it's very cheap, easy to manufacture. Okay. Go on to the motivation. I think it's pretty much agreed by almost everybody that robotic hands have developed significantly over the past couple of years, but they're not quite to the level of human hands. And we part the simple assumption, if they're a bit more similar to human hands, maybe they will improve in quality. Maybe they'll get better grasping. So how can we capture this complexity in robotic hands? Couple theories have been developed. I've been covering 3. So sorry for the large info dump. First, we just break down into synergies. Synergies can refer to a bunch of stuff. In this context, they just refer as an organized pattern for the fingers to follow, instead of a random motion or just flows. When we talk about synergies, every joint of the finger, of the hand, follows sort of a target plan that is supposed to be good. In this work, with padding from this paper by Santello, he tested a lot of people grasping objects, recording how the hand moves while grasping, and establishes first, second synergies. The first describes the general grasping action. Second, essentially acts as a modifier that can be combined and defines a space so that you can have a different range of graspings. I think only the first 2 correspond to 80% of all the hand configurations humans do when grasping stuff. So we can summarize a lot of information in little things. We go from 15, 16 degrees of freedom to 2 if we do this in a smart manner. That is for the hand. For the actual mechanisms, so really nice paper. Catalano et al. Classifies different papers, strategies to control robotic hands. We work for full actuation. Every joint has a motor. Very difficult, very annoying to program. VSA stands for, what does it stand for? Sorry, it's been a little bit. Variable stiffness actuation. It's simply adding an elastic component to the joint. So you actually have a little bit of compliance to the motor. And after I'm actuated, so it's the stiffness, variable stiffness is the first key component. Make your stuff able to go back and forth a little bit. Second is under actuated components. Different elements of the hand are able to compensate for each other. For example, the classic example is that if a finger locks, the whole hand doesn't lock, but the other fingers allow to compensate for each other. We have variable stiffness, compensation, and of course the synergies. And he also describes different strategies. We part from rigid synergies. You can imagine a hard hand just following this predefined set of motions, and we can combine it. We can combine it with the other components. Synergies with this elastic element, and synergies with elastic element and under actuation. So you could, in theory, you could have all of this. And it has been done. Here we have one of the most popular examples, Visa IT hand. The red one is the first prototype. Second is the second one. This is a very popular hand that is used in research and is used in some commercial applications, and it's very successful. And it implements all of these 3. The first one in red is locked to a single synergy, I believe. So it's under-actuated, it's soft, it follows that synergy, follows one. And the second one actually has a space where you can follow this multiple on one, and with just 2 motors, you have this very impressive degree of control. We do get a tiny problem, however, in that designing this and building them, it is very complex. I can barely understand the paper for this. It takes account the intrinsic frictions of the joints, and I'm an electronics student. I have no idea what's going on. So my core question while developing this is, can we maintain this very nice, complex behavior in a simple mechanical way? And this leads to the core proposal. Instead of having this multiple mechanisms with weird interconnections, I'm just going to embed everything into the material. First, we selected an end effector. I parted from this very nice fingers from Italian paper. Super simple. You pull a string, finger collapses, you release it, the material wants to return to its normal structural shape. And it's been used by people to make like some really nice adapters in a very simple manner. If we look back into our classification, it will fit here. It is definitely it is definitely soft. It can be configured to compensate. So back, if you connect two together, a finger can compensate for each other, but it doesn't feature any synergies. It's just a dumb slab that just wants to close or to open. So the project is essentially summarizing how can we add embedded intelligence to these things. I broke it into three parts. First, I was going to take a simulation approach because stuff easy, because it's something I'm more familiar with. So essentially, it was the process turned into, I'm going to make a digital twin of this. I'm going to calibrate it. I'm going to take material specifications, and I'm going to make a digital twin. Then I will take that digital twin. I'm going to identify some key parameters, and I'm going to tweak them so that eventually will converge onto the result that I want. And when that is done, I validate it, and I build a hand with that. Step one, how do we make a digital twin for this? I did a very small modification for this. I essentially just added a joint, making it slightly more anthropomorphic, and some minor modifications to the building process. Then a lot of fun, experimental setup, measure what happens if I put X force and X distance, what happens to the finger, make some marks, get the angles, painstakingly go through more than 300 images and note each point, get the angles, and eventually move into a digital equivalent. I was using a software called SOFA with a soft robotics toolkit. Very nice. It gets you quite accurate results, and it also allows you to mess in real time, which we'll see later. Can be used for some neat things. And after painstaking validation, we can see very nice correspondence. Not perfect, but close enough. Here we have the curves. Main difference is that the fingers, well, they have friction, and I just assume frictionless effector on the other one. Maybe not the best approach. That's about it. We can still see that despite it having slight hysteresis, slight difference between moving forward backwards, the simulation in green is still bounded by the other ones, which I assume to be good enough. We will see that up to a point before the fingers close. It is sort of linear. That simplifies a lot of stuff. Quasi-linear, at least to a point. Okay, we have a digital finger. Let's optimize it. It's a simple structure, so we can identify some parameters that we say, oh, if I change this, this is likely to happen. If I change the aperture of this and the thickness, I can see how sections of the finger will move more or less depending on how much I pull. So we can say, oh, there's a ratio between the movement of successive joints, and depending if I make them thicker or lighter or thinner, they're going to move in different ways. And the goal is to tune for this case, to relationships between successive joints. Okay. We started by defining some fixed variables, anatomical stuff. Just get into papers, get data from real fingers, and tweak between these control parameters. Just go, get the simulation, get the ratios in simulation, and as long as they fill an error criteria, I just want a 10% error, and for the values to be bounded by something, I will accept them. 20 iterations, get to convergence, not perfect, but between my error estimates. And we can see here the comparison between result, finally real assembled finger against the simulation, where all the results still within range. Worst case was 126% error, and everything else below the 10% mark. Okay, now the actual stuff. We have fingers that have been apparently calibrated up to a synergy. We can do a quick test on the simulation engine, which is one of the nice things about SOFA. We can actually do grasping test, and now we move on to design an actual hand. So here, it's right here. Here we have final hand, 3D printed materials, silicone fingers, laser cut acrylic. Everything is extremely cheap, like 40 pounds to build one of these. Take that piece of hand. Of course, it is still significant. It's definitely not to the level. Yes. Yeah. Very simple. It uses an actuation block to pull all the fingers. You can slightly adjust the tensions for everything, and it provides a very simple platform to try different stuff. We did some standardized testing on this, YCB grasping test, different selection of items, kindly led by the grasping team, and some force test. We got some really interesting conclusions. The hand is has a surprisingly big grasping force in the distal direction, so like this. Very weak radially. So if I were to grab, I don't know, phone, it's very weak in this direction. Fingers just rotate out of position. Main conclusions probably because this thing doesn't have bones. It's just essentially meat. So this was the core contribution as presented in this conference, mainly two. We have a methodology that can be generalized for embedding synergies onto stuff in a very simple manner. The simulations system is quite nice because it doesn't mean I need to use this square horrifying fingers. I could use realistic ones if I wanted to, and it will be the plan eventually. And the second one is that we have a very cheap to produce hand that could be applied to different stuff. Normally, for future works, I'm actually going to skip this one because now we actually can move on to the short-term developments as of this thing was presented. I might have been lying to you a little bit during this presentation because the original application for this was not competing against a leading hand in the industry. It was actually to prepare a prosthetic device that could be used to improve on a prosthetic device. This is the Phoenix hand. It is a common 3D printed hand that is completely passive. Simply, if a person has suffered an amputation, let's say has the fingers but still has a stump, they simply put 3D print this, sizes to the requisites, put their hand in there, and by moving the wrist, they can close the fingers. And you can see how that inspired the mechanism in mind. The original project was actually to implement this, to implement the soft fingers onto a prosthetic, and everything sort of spiraled from there. We have some really bad initial prototypes, and then we tried to make them a little bit better, which led to the embedding of the synergies. Did it work at the end? Have questions. It's definitely still not ready to give this to a person. But I could see this part into two ways. First one, come on in time. It's so good. First one, keep following this area of this approach for the prosthetic. Get this one published, do user studies, refine it, see how can we improve onto this. I quite like that it's very human, unlike the original one, but it does not perform as well in actual grasping tests. A different approach to completely abandon the prosthetic, as I did on this, and just focus on robot interaction, which I think also could lead to some very interesting routes to explore. How can we? It's that soft hand that we can just give to a robot, and it can just grab stuff, and it'll be fine. We're not scared of making this thing. Yeah. So, tiny past achievements for the past couple years, for the past year. First, we had a team of master students working on adding multiple degrees of freedom to this. Since everything is just a silicon structure, it is actually really easy to add more systems instead of doing a whole synergy at the same time. You can just separate different components. So we have this correlate motion in fingers. We also have this, and we can go side to side. And this is a finger that I broke, but that does the same. If I pull one, it does the same up and forth. And if I pull the other one, it does the complete curling motion. And you can see how the linear combination of this will lead to the whole span. You can also do side to side. It's a bit better when it was not broken. It's very nice because it involves minimal complexity added to this. It's just adding more tubes onto silicon, which is it will be significantly more difficult in traditional mechanisms. We have a student with Dr. Apollinaire working on a wrist for this, because something quite nice about this is that right now it only has a single synergy, but there we go. If I pull the block out, I can actually move it to the side instead of the rail. And you can see how this starts to look closer to other synergies. So if we add another degree of freedom here, maybe we can get a similar result and multiple synergies. This work was also submitted for the image competition, Student of the Year Mechatronics. It doesn't say accepted. Yeah. I'm also hiring, not quite. You will get at zero money if you accept this, but there's a lot of works that we would like to do with this. Structural improvements, adding bones, maybe anisotropic materials will be a better option. How can we improve the structure? How can we improve other properties? Control, we might have a student working on this, unconfirmed. How different ways to add control systems to this. The synergies we can use, direct control, we can use the pooling system. There's so many cool things we can do this. So yeah, right now, technically, everything is soft synergies because it doesn't have a differential mechanism. It doesn't quite reach this. But it will be actually not that difficult. We have a prototype before that did. We just did little difference since the fingers are so soft that we just ended up discarding the adaptive part. Keeping on. It also offers a really nice opportunity to add sensing. For example, everything is silicon. You can just embed a flex sensor on the inside, combine that with control and get closed loop control. You can embed other sensors, tactile, I don't know. And how can we add the multiple synergies that I mentioned? Okay. This has been me ranting for 20 minutes. I think that's it. Thank you very much for your attention. Hope you enjoyed your presentation. Okay. Any questions? Yes.
Yeah, great talk. Like project. Appreciate that.
Very, very likely. If I were to do everything again, I probably wouldn't. If I were to keep with this structure, I wouldn't opt for the simulation approach that I use. I probably just do a normal characterization. We have discussed with a couple of people, oh, I want adding bones will be interesting. Adding anisotropic materials might be better. There's a point that I'm not sure until we try, to be fair. But yeah, I do expect adding bones might affect the ratios. Maybe we need to come up with something different. I think the main advantage of this thing is that it's simple to manufacture. So ideally, at the end, you will just have a mold, put the bones there, cover in silicone, and somehow it will work. So unfortunately, we won't know until we try. I would love to people try it though. Any other question?
So in one of the models, you showed the VSA, the variable stiffness actuator.
Yeah.
Model E. Did you actually measure the stiffness when it's grasping different objects?
No.
No.
Okay. I didn't measure it.
But is there a belief that different shapes of objects being grasped, the stiffness is changing within the? Is that the?
In other hands, well, in mine, it doesn't take that into account. It definitely does, however, change the stiffness. I've shown you before this graph of the input distance.
Yeah.
Versus, yeah, showing input distance versus angle displacement of the fingers. That is for distance versus angle. This is force versus angle. You can see ridiculous amount of hysteresis at some points, frankly. It was a significant challenge at the beginning. So there's definitely a stiffness response onto this. Can we manipulate it to do something useful? It will be nice if the fingers become rigid when you're actually force.
The reason I'm asking, they're working on legged robots.
Yeah.
And this is one of the
Very good question. Yep.
I wasn't sure about how you did the fitting of the synergies. You were fitting the data in the model. So it wasn't different fingers, right? It was you measuring it from hand data, or
yes, I'll go over it and over it. Actually, do I have it on the last slide? No. The core paper that I use, this one, it will be. Can I just quickly just do this, because it really has some very nice figures that we can show. They scan a lot of people. Give me a PDF. They recorded a lot of people grasping different tools, different objects. PDF. And they using principal component analysis. They separated everything into different techniques, and they essentially constructed a linearized version at the end. Oh, here's how much every joint moves relative to each one. So for example, when you grab something, this moves 1. This moves twice as much. This one's half as much, something like that. I extracted that data. I did some rounding. So, in some ways, I was just limited by the material. If something is moving, I think one example, a joint was moving 9 times more than the other. And so I have to say, no, I'll do 3 times. And so I got those numbers, and here in the somewhere, and those numbers will be my case. There will be a K or a ratio or relationship per finger. So I got a K per finger. It's actually, I can show you the papers because it's all in there. And I then do my optimization process. Okay, we increase the thickness in one segment. We decrease the thickness in one segment. We change the aperture of the fingers until it's close enough to that ratio. And I say, okay, we have convergence. Yeah. That's a really good question to you.
quite a long process.
Yeah. Yes.
Just to follow up, that was finger by finger.
Yeah.
Is there anything?
Excellent question. I optimize each finger independently, and I said, okay, I'm bounding my K I'm bounding my K by a angle per Newton ratio. It does lead to some inconsistencies, because in some case it could be that, oh, a whole finger is relative, is normalized with respect to, it's also normalized with respect to the end. So it could be that in one finger is normalized with respect to 1. In the next one, it could be normalized with respect to 2. So it could be that finger. It's noticeable in the final prototype, but it's definitely marked as in the next iterations, everything should be, this shouldn't be bounded. We should just say, oh, the final one is going to move with this ratio to keep consistency. That is a very good observation. So, yeah. Okay. Thank you very much.